Okay, buffers. So we have been looking up till this point. Up till this point, we've been looking at mixtures of strong acids and strong bases. Now, when we have a buffer is a mixture not of strong acids and strong bases. It is a mixture of a weak acid and its conjugate weak base. And they don't do anything quite so tidy as just react with one another and neutralize. They form, because they are weak, we're going to get an equilibrium. And because we have an equilibrium, equilibria can shift. So an equilibrium shifts in order to do what?
Relieve a stress.
Relieve a stress, yes. Okay. And I'm actually, in this case, I'm going to word it a little differently. I'm going to say in order to minimize the stress. And so buffers, because we're dealing with weak acids and weak bases, we're going to be dealing with hydrogen and we're going to be dealing with hydroxides, okay? And the stress in this case is going to be either to this system of our weak acid and conjugate base, we're going to be adding a small amount of acid or base. So the stress is going to be a small additional amount of H plus, maybe we add some HCl to our system, or a small amount of OH minus, so maybe we add some sodium hydroxide. And so if we add a small amount of H plus to our system and the equilibrium shifts in order to minimize that stress, we won't actually end up with much more H plus than we had before. And if we have a very small, tiny difference in H plus, then our pH doesn't change very much. So the purpose of a buffer is to minimize changes in pH. Okay, and if it's minimizing changes in pH, that also means that it's minimizing changes in POH, concentration of hydrogen, and concentration of hydroxide. Okie dokie. So that is why a buffer is, and that is what a buffer is. So let's look at an example of a buffer. So we're going to take some acetic acid. Oh, I should write it in red because it's an acid. Why not? Sounds good. CH3COOH. That is our weak acid. And it's going to be in equilibrium with its conjugate base, CH3, COO minus, and H plus. Okay, so here we have our weak acid, we have our conjugate base. And so if we were to add a small amount of OH minus to the system, what does OH minus do to that system? OH minus is going to cause the system to Daniel, you're right. Yeah. 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 It's going to shift to the right because we're going to have our H plus and our OH minus. Those are going to get together and they are going to form H2O. And if that's the case, what that means is that the concentration of hydrogen decreases and the system shifts to the right. So if we were to draw a graph then of what is happening to the concentration of hydrogen, there's our concentration of hydrogen, and on the right, let's see, we have time here. Initially, we have our equilibrium, so the concentration of hydrogen is constant. And then we add some base, so the concentration of hydrogen decreases. However, when it decreases, the system shifts right in order to bring the concentration back up to not quite its original value, but close, okay? So the final concentration of hydrogen is very close to its original value. That means that this system has minimized the change in H plus, right? We don't have a change that's that much. We have a change that's only that much, little tiny change, okay? So the actual change in the concentration of H plus is tiny, okay? So this system has minimized the change in the concentration of H plus. And so in other words, i.e., the system has minimized the change in the concentration of, change in pH, because pH, of course, is related to the concentration of hydrogen. And that is what a buffer does. Okay. Now, what if we add a small amount of HCl, that's a strong acid, to the system? And I'm going to draw the system again down here because it's too far up. CH3, COOH in equilibrium with CH3, COO minus plus H plus. So what's going to happen if we add some HCl? Shift right, shift left. Got a couple shift lefts, a shift right. No one else wants to chime in? Okay. So yeah, we have added HCl. The HCl, of course, dissociates into H plus and Cl minus. So our concentration of H plus goes up, and that's going to cause the system to shift to the left. Okay. And if we were to draw our graph for this one, what it would look like is we would have, here's our concentration of H plus. Initially, we would have a constant concentration of H plus. There's our time. Here we add HCl. So initially, oh my goodness, there's a huge spike in the concentration of hydrogen, which means our pH is initially, just for a moment, it's going to go way, way down. Remember, as hydrogen concentration goes up, pH goes down. But then after that initial spike, the system's going to shift and we'll use up the H plus until it's almost back to its original value. Okay, so we have minimized, the system has minimized the change in concentration of H plus, and therefore it has minimized it's doing weird things. There we go. Minimized the change in the pH. So that's the general theory behind a buffer. Okay, nothing magical about it. It's just an equilibrium that shifts and minimizes the stress. The only hitch is that you actually have to go to the trouble of adding enough of the acid and enough of the conjugate base that you don't run out of one of them as the system is trying to shift. Okay, so this is a key point here. A buffer system must have enough of both the weak acid and the conjugate base that you don't run out of one of them while the system is trying to shift. Okay, so let's imagine that you tried to make a buffer and you're like, okay, I am gonna make a buffer and I'm gonna make it with that acetic acid. And so I'm just gonna put in a decent amount of acetic acid and I'm gonna add acetic acid, CH3, COOH to a beaker. And I say, yay, buffer, I've made it. And you might think, okay, yeah, sure, I've made a buffer because, if I write the equilibrium, if I've added this to a beaker, it's going to be that same equilibrium, CH3COOH, in equilibrium with CH3COO minus plus H plus. Okay, and that's great. And let's say I added enough so that I had, I don't know, 0.5 molar. Okay. Well, if I have 0.5 molar acetic acid, what concentration of acetate do I have? If we have 0.5 molar CH3COOH, what is the concentration of acetate? Okay, we can do that finding using a race table. 0.500 plus x minus x. 0.500. Oh, that looked terrible. 0 minus x. And then we have an x here and an x here. And of course, we're going to have then our Ka equals CH3COO minus times H plus over CH3COOH, which is going to equal, in fact, I'm just going to rewrite the whole dang thing. That's 1.8 times 10 to the minus 5 is the value of Ka, and then we have x squared, and let's assume x is insignificant. Okay, so that's x squared over 0.5. And toss that in the calculator. 1.8 times 10 to the minus 5 times 0.5 is, take the square root of that, and we get, so then x is equal to 0.003 molar. Okay? So what that means is that our concentration of acetate is 0.003 molar, and our concentration of acetic acid is 0.5 molar. So once again, I'm going to write that equilibrium again. Okay. There we go. CH3, COOH in equilibrium with CH3, COO minus plus H plus. And our concentration here is 0.5 molar, and our concentration here is whoops, why are you not writing? 0.003 molar. Now, what if I add some extra HCl, okay? And that's going to be at a concentration of 0.01, whoops, 0.01 molar. Can you see that this is going to be a problem? Because this number, 0.01 molar, I've now increased this concentration. So the system is going to want to shift this way, and it's going to want to use up most of this. Yeah? The problem is that in order to use it up, the hydrogen has to react with the acetate. And we have more hydrogen than we have acetate. Yeah? So by adding this extra H plus, we're actually going to overwhelm this system, and it's not going to be able to shift all the way to the left to absorb the extra hydrogen. So what our graph would look like for that one is here's our concentration of hydrogen. Here's time. Okay, we start it with our normal concentration of hydrogen. And then we add our extra HCl. And then the system starts to shift. Do, 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 do. And then we run out of acetate. Okay, right here, we run out of CH3COO minus. There was not enough to absorb all the extra acid. All the extra H plus. Okay, and the moral of this story, you're not going to have to do calculations like this or anything. I just did this to prove the moral of the story is you cannot make a buffer just by adding a weak acid to the solution. What you would have to actually do is to make a buffer, you must add individually the weak acid. So that would be our CH3COOH molecules. So we would have a lot of that CH3COOH. And the second thing you need to do is you need to add the weak base. Okay? And in this case, that would be CH3COO minus. So you have to add them like from separate containers. You'd take a container that has your acetic acid, throw it in. You'd take a container that has your weak base, the CH3COO minus, and you'd throw it in. So you end up with lots. You would have lots of the CH3COOH, and you would have lots of the CH3COO minus. And just so you know, we cannot go to the back storage closet and get some acetate ion on its own. Ions don't come on their own, so we cannot just add a weak base. We actually have to add the salt of the weak. Ooh, and I should put in conjugate there as well. Conjugate base. Okay, so instead of just adding CH3COO minus, we would add the salt. In this case, I'm going to make it a sodium salt, CH3COO, or it could be potassium, CH3COO. Any of your alkali metal salts are good because alkali metal salts are always soluble. Okay, so anytime you're making a buffer, you have to have a weak acid, you have to have the salt of the conjugate base. The only exception to that is when you have a weak base and the salt of its conjugate, acid. So let's write a summary of what buffers are. Buffers are either, buffers are mixtures of either A, a weak acid, and the salt of its conjugate base, or B, a weak base and the salt of its conjugate acid. For the purposes of chemistry 12, this is not exactly true, but it's close enough for chemistry 12. This will give you what they call an acidic buffer, and it buffers at pHs less than 7. Okay, so if you want to maintain a pH fairly constant at about pH 6, you're going to use a weak acid and the salt of its conjugate base. If you want to buffer at pH 5, you're going to use a weak acid and the salt of its conjugate base. Because you're buffering at pH less than 7, you're going to use the weak acid and the salt of its conjugate base. If you've used a weak base and the salt of its conjugate acid, you're going to have a basic buffer. Okay, and that's going to buffer at pH greater than 7. So if you want to buffer a solution and have it stay relatively constant at pH 8 or pH 10 or pH 7.5, you're going to use a weak base and the salt of its conjugate acid. And I know we haven't done an example like that. A weak base, maybe for example, we have 0.5 molar NH3, that's our weak base. Who is the conjugate acid of NH3? NH4, yeah. Okay, so its conjugate acid is NH4 plus, but we don't just want the conjugate acid, we want the salt of its conjugate acid. And so we just need to put it in a compound. So we're going to have 0.5 molar, remember, because we need to have a large amount of each, right? We don't want to have like 0.5 molar here and 0.002 molar over here. We want to have large quantities of both so we don't run out, okay, while it's shifting. This is going to be NH4, and what's a good thing to pair it with? You could make it NH4Cl, okay? You could make it NH4NO3. Just make sure you have paired it with an anion that does not hydrolyze. Okay, and the Cl minus is good because its conjugate acid is HCl, which is strong. And so Cl minus won't hydrolyze. NO3 is also good because HNO3 is strong and it will not hydrolyze. Okay. And I think the last thing is just we've really focused on the fact that we need this weak acid and its conjugate base. They both need to be present in big quantities. So let's just put a note there. Both acid and base must be present in large concentrations. Everyone wants to know what's a large concentration. For the purposes of this, let's say, maybe greater than 0. I don't know, 1 molar, okay? Greater than or equal to zero point 0.1 molar. 0.1 is sort of, anything less than that, and you start to get in the range of, oh, I've overwhelmed my buffer. I've run out of a species, okay? And don't forget that they have to be weak. You cannot bake a buffer with a strong acid or base because the strong acid or base, why not? Why can't we make a buffer with a strong acid or base? What do you guys think? Yeah, absolutely. They do. They dissociate completely. They can't go to equilibrium. Yeah, so if you're like, oh, yeah, excellent, I'm going to have my HCl and I'm going to have my salt of my conjugate base. I'm going to add some NaCl. You're like, okay, woo, here I go. Well, if I add hydroxide to that, the H plus will neutralize hydroxide. But if I start adding hydrogen, this system cannot shift because it just doesn't go that way. So you cannot make it with a strong acid because there is no equilibrium to shift. Okay? And that is really about it for buffers. And that's been a long lesson. Do we feel like we're good for today?